So the question is symmetric tree, and you are given a node, tree node, and to check is the tree is mirror of itself. And my idea is using a recursive, and there's another method use prefer search. So let's try the recursive first. So if the root equal to null, I just return false. Else I use a helper function to check left and right. And when so recursive has a base case when both are null, which means they are on the lowest level, which is equal to null. I mean it's below the leaf, so when left equal to null and right equal to null, in this case you return true because they are the same. What happens when one of them is null, the other one is not? So if left equal to null, one of them, right? So this will return false. We also have to check is the mirror, if they are mirror. So if the left val is not equal to right val, we return false. Now we're doing the recursive, right? We have the base case right here, and then we do a recursive. So what should we do? When we at this level, the node of this node of right has to equal to this node of left. When this node of left, it has to be equal to node of right, right? So left dot right, comma right dot left, and has to be n, right? Left dot left, right dot right. So let's see. Make sure it's, I mean the name could be better, but it would be super easy to say left and right at this scenario. Okay, so we just did a recursive method, right? Okay, let's start the prefer search. So when we're doing a prefer search, we have to check is the sum of children of one is children of one left and right are the same. If they are the same, then we check is the children of the first two, the first two right is equal to the second of left, and second of first of left is equal to second of right. So okay, let's get it. So let's get a Q and then tree node, and let's just say Q, and we are using a linked list to store it. And when we doing the prefer search, we need the we need to add the node. But when we add a node, we cannot just add one, because we will get a problem when we pop up inside the while loop. So you understand what happened later. The Q add root. So this is a tricky way. So while Q is empty and tree no, sum 1 equal to Q poll, sum 2 equal to Q poll. So if sum 1, so the problem is will be the same if sum 1 and sum 2 are null. We don't care about it. But if one of them is equal to true, return false, and the value is not equal to each other, so we return false. So in this case we need to add so Q dot add. So we need to add the right sum1.right. When we add this, we need to add sum2.left. So this is sum1, this is sum2. When we add 4, we need to add 4. When we add 3, we need to add 3. So this is why we need the two adding for the root, 2 elements for the root first, for the first scenario. But when we doing the while loop, we don't. And sum1.left equal to sum2.right. So you get the idea, right? Why we need to add 2 for the root, because when you don't do that, you cannot going on the right and going on the left inside the while loop when we poll. So let's try to run it. Oh, I forgot to return something. So return, what do we need to return? We return true if they are all match. Yeah, if they are all match. So yes. Okay, so you will see like using the breadth search, you will get a little bit slower. So the idea is you add 2 elements inside your queue for the root, because you need to poll for the children later, since the binary tree has 2 children for each node, and when you poll, you have to poll twice each time. So this is the only trick. Other than that, I mean, the time and space complexity for this one will be O of n for the time, and the space will be O of n as well, because you're adding the node to the queue, and then the recursors, I think just O of n for time, and then space is nothing. So that will be it.